A secure authentication gate snaps open when presented with a specific string. The system's internal logic is subverted, granting entry without a valid password. This is SQL injection. The attack occurs when a backend database is tricked into treating user-provided text as part of its own executable command set. The vulnerability exists because of an architectural confusion between data and code. A developer designs an input field to receive a name or a password. However, a vulnerable application treats that input as raw text to be blindly incorporated into a larger set of instructions. If the application fails to distinguish between a name and a command, the database engine will execute whatever instructions the attacker manages to insert. We will now deconstruct the logic of an injection payload, track its delivery over the network, and implement the structural code changes required to permanently eradicate the threat. SQL injection represents a failure of structural logic, where the rules governing the application's internal grammar are turned against the security of the database. This is a standard query for authentication. Blue text represents the database instructions, while orange variables represent user data. In a legitimate login attempt, the application replaces these variables with standard text strings, like a username and password. To break this structure, an attacker provides a payload, a single quote, the word or, 1 equals 1, and a double dash. The initial quote closes the intended string parameter. The remainder is treated as an instruction, shifting to blue executable syntax. This command introduces an OR logic gate. In Boolean logic, if the condition on either side of an OR statement is true, the entire statement evaluates to true. The payload follows this gate with the equation 1 equals 1. This is a tautology, a mathematical statement that is universally and objectively true. Because 1 equals 1 is always true, the OR gate forces the entire username check to return a true result, regardless of the actual username provided. The attacker must still address the mandatory password check. The double dash functions as a comment operator. It tells the database to ignore everything that follows it, effectively deleting the password requirement from the execution plan. The manipulated query is now reduced to a single guaranteed condition, asking the database to find any user where true equals true. With the query evaluating as true for every entry, the database generates a result set containing every user in the system. The application backend typically processes the first record on that list, which is almost always the system administrator, and grants full access. The database permits administrative access without verifying a password. The attacker has gained entry by weaponizing the system's own logical requirements against itself. Before this logic can be executed on the backend, it must travel from the attacker's browser to the web server. Browsers traditionally use the HTTP GET method to request data and transmit variables. A GET request appends user input directly into the URL string, making the parameters visible in the browser's address bar. Because the input is exposed, an attacker can manually type and manipulate injection payloads directly in the URL. As an alternative, many developers use the HTTP POST method for sensitive data like login credentials. A POST request places the input inside the body of the HTTP message. To a casual observer, the URL remains short and clean, even though the malicious payload is still being transmitted in the background. This visibility difference leads many to believe that switching from GET to POST constitutes a security upgrade. In reality, the backend SQL engine does not differentiate between how the data arrived. It evaluates the incoming input identically, regardless of the transport method. If the backend code uses string concatenation to build its queries, both GET and POST methods remain equally vulnerable to injection. Hiding the payload provides only an illusion of security. Real protection requires a structural change in how the database processes the data once it arrives. Preventing SQL injection requires a structural change. This is achieved through prepared statements, using dedicated methods to prepare and bind information. In this execution flow, the first step is pre-compilation. The application sends the query's structural skeleton to the database before any user data is added. This skeleton locks into place inside the engine. The database compiles this structure, treating the variable positions as strictly empty placeholders. Then the user's input drops into the reserved placeholder. Notice that the entire payload remains orange. Because the execution plan is already locked, the database engine refuses to parse the new data as executable syntax. The single quotes, logic gates, and comment dashes lose all authority. The engine treats the entire malicious payload as a literal text string, exactly as it would handle a standard name. Parameterization fixes the root vulnerability by physically separating the instruction phase from the data processing phase, making logic manipulation impossible. We can now revisit the initial login attempt against this secured architecture. The attacker submits the same payload, a quote, an OR gate, and the equation 1 equals 1. Under the rules of a prepared statement, the database searches for a user whose literal actual name is that exact string of characters. It finds no match. The system rejects the login attempt, and the system remains secure. SQL injection thrives when systems confuse data with instructions. By enforcing structural isolation between the two, developers can neutralize the threat and secure their application logic permanently.